Right now, you are moving. You're sitting still, maybe lying in bed, maybe on a couch. But right now, you are hurtling through space at over 1.3 million miles per hour. You are on a rock orbiting a star, inside a galaxy, inside a supercluster, inside a web of structures so vast that if you tried to cross it, even at the speed of light, you would die before you got anywhere close to the other side. And here's the part that should really keep you up at night. Most of the universe is already gone. We will never reach it. We will never see what is happening there right now. It has been swallowed by the expansion of space itself. Stay with me. Because by the end of this, the way you look at the night sky will never be the same. Before we continue, make sure to like and subscribe if you enjoy relaxing science documentaries and fascinating journeys through the universe. Now settle in, get comfortable, and let's discover why everything around us is constantly in motion. Part 2. Let me start with a number. 93 billion. That is the diameter of the observable universe in light years. Now I want you to really sit with that for a second, because I do not think any of us, not me, not the most brilliant physicist alive, actually feels what that number means in our bones. A light year is not a unit of time. It is a unit of distance. It is how far light travels in one full year. And light, moving at 186,000 miles every single second, covers about 5.88 trillion miles in a year. So 93 billion light years means 93 billion times 5.88 trillion miles. I will not make you do that math. The answer is a number so large it does not fit comfortably inside human language. But here is where it gets strange. The universe is only about 13.8 billion years old. So how can the observable universe be 93 billion light years across if nothing can travel faster than light and light has only had 13.8 billion years to move? The answer is that space itself is expanding. The fabric of reality has been stretching since the very first moment of creation. And because of that stretching, light that left certain regions billions of years ago has been carried further and further away from us, even while it was traveling toward us. Think of it like walking towards someone on a moving walkway that is going in the opposite direction. You are moving forward, but the ground beneath them is sliding away. So even though light has been rushing toward us for billions of years, the point it came from has been carried billions of light years further away in the meantime. That is just the observable universe. The part we can see, the actual universe, might be infinite. Some models in cosmology suggest the universe extends forever in every direction. Others suggest it is merely unimaginably large but finite. And here is the terrifying thing. We cannot tell the difference from where we are standing, because everything beyond the observable boundary is hidden, not by a wall, not by a fog, but by time itself. The light from those regions has simply not had enough time to reach us yet. Now let us come back down to something a little closer to home before we zoom all the way back out. Let us talk about our solar system. Because even that, the tiny little neighborhood we live in, the place we have sent actual human-made machines to explore, is already so staggeringly large that it breaks our ability to picture it. And once you understand the solar system at its true scale, interstellar space, the galaxy, the universe, all of it, it starts to hit differently, not as numbers on a page, but as a physical feeling. A kind of beautiful, vertiginous awe. So that is where we are going to begin. We are going to start with what is right here, and we are going to zoom out step by step until we hit the edge of what we will ever be able to know. Buckle in. Part 3. The solar system. Picture the solar system the way you probably saw it in a textbook. The sun in the middle. Mercury, Venus, Earth, Mars bunched up close together. Then the asteroid belt. Then the gas giants. Jupiter, Saturn, Uranus, Neptune. And then nothing. Empty space. That picture is a lie. Not intentionally, but it is wrong in almost every way that matters. The distances between planets in those diagrams are compressed enormously. Because if you drew the solar system to scale on a single page, with the sun the size of a dot, Earth would be a speck barely visible to the naked eye, and Neptune would be somewhere off the page entirely. Let us do this properly. Imagine the sun is the size of a basketball, about 9 inches across. At that scale, Earth would be a grain of sand, about 1 millimeter in diameter, and it would be located about 86 feet away from your basketball sun, the length of most people's backyards. Maybe a little farther. Mars would be a slightly smaller grain of sand, about 130 feet away. Jupiter, the largest planet in our solar system, would be a small marble, about 10 millimeters across, but it would be 447 feet away from the sun, further than a football field. Saturn, that stunning ringed giant, would be another marble, 820 feet away. Uranus, over a quarter mile away. Neptune, the furthest of the 8 planets, 1.4 miles away, 1.5 miles from your basketball sun, just to reach the edge of the known planets. And we have actually sent a spacecraft there. Voyager 2, launched in 1977. It reached Neptune in 1989, after a 12-year journey. Voyager 2 is our only spacecraft to have done a flyby of all 4 gas giants, Jupiter, Saturn, Uranus, and Neptune. Now here is where it gets interesting. Most people think Neptune is the edge of the solar system. It is not even close. Beyond Neptune lies the Kuiper Belt, a vast region of ice, rock, and debris that stretches from about 30 to 50 astronomical units from the Sun. An astronomical unit is the distance from the Earth to the Sun, about 93 million miles, so the Kuiper Belt extends from 30 to 50 times that distance. Pluto, which was demoted from planethood in 2006, much to the heartbreak of an entire generation of schoolchildren, lives in the Kuiper Belt. It was reclassified as a dwarf planet because we discovered it was not alone out there. There are hundreds of thousands of other icy bodies in the Kuiper Belt. Some of them are comparably sized to Pluto. In 2015, NASA's New Horizons probe flew by Pluto and sent back stunning images. Mountains of ice, a heart-shaped nitrogen plain, a hazy atmosphere. Pluto turned out to be a complex, beautiful, surprising world. It took New Horizons 9.5 years to get there. 9.5 years. At speeds of about 36,000 miles per hour, to reach Pluto, which is not even the edge of our solar system. But even the Kuiper Belt is not where the solar system ends. Surrounding the entire solar system, like an enormous spherical shell of frozen debris, is the Oort Cloud. The Oort Cloud is where the long-period comets come from. Those dramatic comets that streak across our sky once every thousands of years. Comets with orbital periods so long they were circling the sun before the pyramids were built, and they will circle it again long after everything we have ever created has crumbled to dust. The Oort Cloud is thought to extend from about 2,000 astronomical units all the way out to perhaps 100,000 astronomical units from the sun. Let me put that in terms our basketball model can handle. If the sun is a basketball and Neptune is 1.4 miles away, the inner edge of the Oort Cloud would be at about 57 miles away, and the outer edge would be somewhere between 1,700 and 2,800 miles away. On our basketball sun model, the solar system extends to nearly the distance of a cross-country drive across America, and we have never sent a single spacecraft into the Oort Cloud. Not one. It is so far away that even Voyager 1, the most distant human-made object ever, the spacecraft we launched in 1977, which has been traveling for nearly 50 years and is now more than 15 billion miles from the sun, is still only barely approaching the inner edge of the Oort Cloud. To get to the Oort Cloud, it needs to travel another 300 to 1,000 times its current distance. We have been exploring space for over 60 years. We have put humans on the moon. We have sent robots to Mars. We have touched the sun with a probe. And the edge of our own solar system remains unreachable with any technology we currently have. Now, think about that. And then understand that the nearest star to our sun is not in the Oort Cloud. The nearest star is on the other side of it, and 4.24 light years beyond. Let us zoom out. The void between stars, this is the part of the journey where even language starts to struggle. Between our solar system and the nearest star, Proxima Centauri, there is nothing. Not a thin nothing, not an almost nothing. A profound, absolute nothing. No rocks, no debris, no gas clouds worth mentioning. Just the hard vacuum of interstellar space, stretching on for 4.24 light-years. Now, 4.24 light-years does not sound that big compared to the numbers we will encounter later. But let us put it into terms that our basketball model can appreciate. If the sun is a basketball in your backyard and Neptune is 1.4 miles away, then Proxima Centauri is roughly 700 miles away. On that scale, the next nearest basketball, the next star, is on the other side of the continent, plus the ocean, plus part of another country. A single grain of sand in your backyard, and the next grain of sand is in London. Or farther. In actual miles, the distance to Proxima Centauri is about 25 trillion miles. 25 trillion. That is a 25 followed by 12 zeros. Our fastest spacecraft, the Parker Solar Probe, can reach speeds of up to 430,000 miles per hour. That is extraordinary. That is faster than almost anything we have ever built. At 430,000 miles per hour, it would take about 600 years to reach Proxima Centauri. Longer than all of recorded human history. Voyager 1, our most distant spacecraft, is moving at about 38,000 miles per hour. At that speed, if it were heading toward Proxima Centauri, which it is not, it would arrive in about 73,000 years. Modern humans have only existed for about 300,000 years. We would be sending it now, and it would arrive roughly a quarter of the way through the entire span of human history. And Proxima Centauri is our nearest neighbor. Here is another thought that tends to stop people in their tracks. When we look at Proxima Centauri, the light entering our eyes left that star 4.24 years ago. So we are not seeing the star as it is now. We are seeing it as it was 4 years ago. For stars further away, we are looking back decades, centuries, millennia. When ancient Egyptians looked at some stars in our galaxy, they were seeing light that those stars emitted around the time pharaohs were building pyramids. Distance and time and space are the same thing. You cannot separate them. The further away something is, the further back in time you are looking. This is not metaphor. This is physics. And its implications run deep. But we are not done zooming out. Not even close. We have crossed one gap between stars. Now, let us try to understand what it means that there are 400 billion stars in our galaxy. Part 4. The Milky Way. The Milky Way is our home galaxy. On a clear, dark night, far from city lights, you can see a faint band of light stretching across the sky. That is the glow of hundreds of billions of stars, the arm of our own galaxy seen edge on from our position inside it. And even that view, breathtaking as it is, tells us almost nothing about the true scale of what we are part of. The Milky Way is a barred spiral galaxy. It has a bright central bar structure, with sweeping spiral arms uncoiling outward from the bar's ends. Our solar system sits in one of those arms, called the Orion Arm, sometimes also called the Orion Spur. We are not in the center. We are not on the edge. We are roughly 2/3 of the way out from the center, somewhere in the suburbs of a vast cosmic metropolis. How big is the Milky Way? Estimates have been refined over time, but our galaxy is currently thought to be about 100,000 to 120,000 light-years in diameter. Some recent research suggests it might be even larger, perhaps up to 170,000 or 200,000 light-years across, when you account for the fainter outer disk. Let us put that in perspective. Remember, light travels at 186,000 miles per second. It can circle the Earth 7.5 times in a single second. At that speed, it takes 4.24 years to reach the nearest star. To cross our galaxy from one side to the other, even at the speed of light, would take 100,000 years. Our sun is about 26,000 light-years from the galactic center. So a light beam sent from the center of the Milky Way right now, today, would reach us in 26,000 years, long before our species had written language. And yet, 26,000 light-years is only a fraction of the galaxy's radius. Now here is something that I want you to really absorb. Our sun is one star in the Milky Way, and the Milky Way contains somewhere between 200 billion and 400 billion stars. 200 to 400 billion. And the vast majority of those stars are thought to have planets, not all of them, but most. Which means that when you look up at the night sky, virtually every single point of light you see is a sun. And most of those suns have worlds orbiting them. The number of planets in our galaxy alone is likely in the trillions. And the Milky Way is just one galaxy, one of perhaps 2 trillion galaxies in the observable universe. But we are getting ahead of ourselves. Let us stay in our galaxy a little longer, because there is something at its center that deserves its own moment. Sagittarius, a star. At the heart of the Milky Way, about 26,000 light-years from Earth, there is a monster. It is called Sagittarius A star, and it is a supermassive black hole. The mass of this black hole is approximately 4 million times the mass of our Sun. 4 million solar masses, compressed into a region of space so small that our entire solar system would comfortably fit around it. In 2022, astronomers released the first direct image of Sagittarius A star. It was a landmark moment in human history. We had, for the first time, actually seen the shadow of the black hole at the heart of our own galaxy. The image shows a bright, glowing ring of superheated gas and plasma, swirling around a dark central region. That dark region is the event horizon, the point of no return, the boundary beyond which not even light can escape. Now, I want to be clear. You are in no danger from Sagittarius A star. It is 26,000 light-years away. The nearest black hole to Earth, a small stellar mass black hole called Gaia BH1, discovered in 2022, is about 1/560 light-years away. And it, too, poses no danger. Black holes do not roam the galaxy gobbling things up. They sit in place, governed by gravity, just like everything else. At the distances involved, the gravitational influence of even a supermassive black hole on our solar system is negligible compared to the sun's own gravity. But understanding that there is a 4 million solar mass black hole at the center of our galaxy does something to your sense of scale. It reminds you that the Milky Way is not a calm, gentle place of twinkling lights. It is a violent, dynamic, ancient structure. Stars are born and die. Supernovas explode with the energy of 100 million suns in a fraction of a second. Neutron stars spin hundreds of times per second, beaming radio waves like cosmic lighthouses. And at the center of all of it, pulling everything into a slow orbital dance, is something that warps space-time so severely that not even light can escape its grip. Our sun has been orbiting the center of the Milky Way for its entire 4.6 billion year life. It completes one full orbit roughly every 225 to 250 million years. That orbital period is sometimes called a cosmic year or a galactic year. So the last time our sun was in the same position relative to the galaxy's center as it is right now, the most advanced life on Earth was early dinosaur ancestors. The Triassic period was just beginning. 1 galactic year ago, dinosaurs did not exist yet. 2 galactic years ago, multicellular life was relatively new. We were, in evolutionary terms, very recently figuring out how to have more than one cell. The sun has completed about 20 galactic orbits in its lifetime. And the galaxy itself is much older. The Milky Way is thought to have formed about 13.5 billion years ago, not long after the universe itself was born. When you look at those numbers, our entire civilization, everything from the first campfire to the internet to whatever comes next, fits into a sliver of time so thin that, on the scale of the galaxy's history, we have barely flickered into existence. And yet, here we are, looking up, asking questions. Let us keep zooming out. Part 5. The local group and beyond the Milky Way is not alone. It exists within a small cluster of galaxies called the local group. This gravitationally bound family of galaxies includes about 54 members, ranging from large spiral galaxies like our own to small irregular galaxies and dwarf galaxies. The two largest members of the local group are the Milky Way and the Andromeda Galaxy. Andromeda, formerly designated M31, is a galaxy much like our own, a barred spiral, and it is the most distant object visible to the naked human eye under dark skies. When you look up at Andromeda with your bare eyes, you are seeing the faint smudge of light from a trillion stars over 2.5 million light-years away. 2.5 million light-years. The light entering your eye left Andromeda before our human ancestors walked upright, before our genus Homo even existed. When the light that is touching your eyes right now was emitted, our evolutionary forerunners were living in Africa, and the world would be unrecognizable. And here is something remarkable about Andromeda that most people do not know. It is coming toward us. Andromeda and the Milky Way are on a collision course, moving toward each other at roughly 110 kilometers per second. In about 4.5 billion years, give or take, these two galaxies will merge. Now, before you panic, galaxy collisions are not like the collisions we know from everyday experience. Galaxies are mostly empty space. The individual stars in each galaxy are so far apart from each other that, during the collision, individual stars almost never hit each other. Instead, the two galaxies will pass through each other, and the gravitational interactions will dramatically reshape both of them. The result, over billions of years of gravitational choreography, will be a large elliptical galaxy, sometimes nicknamed Milkomeda or Milkdromeda by astronomers who could not resist. Our Sun and Solar System will likely be flung into a different orbit within the new merged galaxy, but survive the collision essentially intact. But we are not really worried about that right now. Let us step back further. The local group itself is not isolated. It is part of a much larger structure, the Virgo supercluster and Laniakea. Beyond the local group, we have the Virgo supercluster. The Virgo supercluster is a massive region of space containing the local group and dozens of other galaxy groups and clusters. It spans approximately 110 million light-years. It contains somewhere around 1,300 to 2,000 galaxies, organized into galaxy groups and clusters, which are themselves organized into clouds. The Virgo cluster, a dense core of thousands of galaxies at the center of the supercluster, is about 65 million light-years from us. But even the Virgo supercluster turns out to be part of something bigger. In 2014, astronomers published a paper that fundamentally changed our understanding of our cosmic neighborhood. They mapped the gravitational flows of galaxies across a vast region of space, tracing how galaxies move and which gravitational basins they are drawn into. And what they found was that our Virgo supercluster is actually just one lobe of a far more massive supercluster. They named it Laniakea, a Hawaiian word meaning immeasurable heaven. Laniakea spans about 520 million light-years. It contains the mass of approximately 100 quadrillion suns. And it includes about 100,000 galaxies, one of which is ours. Within Laniakea, there is a region called the Great Attractor, a gravitational focal point toward which the Milky Way, Andromeda, and thousands of other galaxies are all slowly flowing. The Great Attractor lies about 150 to 250 million light-years away in the direction of the constellations Centaurus and Norma. We cannot directly see it very well because it sits behind the dense plane of our own galaxy, a region astronomers call the zone of avoidance, where dust and stars in the Milky Way block our view. But we can feel its gravitational pull. Our entire local group and everything within Laniakea is drifting toward the Great Attractor at hundreds of kilometers per second. It is a humbling thing to realize. Our galaxy, our home, is not sitting still in space. It is falling, slowly, gently, on timescales of billions of years, but falling nonetheless. drawn toward a concentration of mass so enormous that it reshapes the flow of an entire supercluster. And Laniakea is not alone either. Surrounding us, at distances of hundreds of millions to billions of light years, are other superclusters. The Perseus-Pisces supercluster, the Coma supercluster, the Shapley supercluster, which is one of the largest known concentrations of galaxies in the observable universe. Laniakea and these neighboring superclusters are themselves part of an even larger structure, the cosmic web. Part 6. The cosmic web pulled back far enough, and the universe reveals its true architecture. At the very largest scales, on the scale of hundreds of millions to billions of light years, the universe is not a smooth, uniform distribution of galaxies. It is organized into a vast, intricate structure that cosmologists call the cosmic web. It looks almost like a spider's web, or the neural network of a brain, or frost spreading across a window. The structure consists of three main components: filaments, long, thread-like structures made of dark matter, gas, and galaxies, stretching across hundreds of millions of light years, connecting galaxy clusters like threads in a web. Walls and sheets, flattened two-dimensional structures where galaxies accumulate, like the walls of a soap bubble network. Nodes, dense intersections where filaments meet, forming massive galaxy clusters, the most gravitationally dense regions in the observable universe. And then, in between all of this, voids. Cosmic voids are enormous regions of space that are almost completely empty. They contain very few galaxies, very little gas, and they span hundreds of millions of light years in diameter. The Boots void, discovered in 1981, is one of the largest known voids. It spans roughly 250 to 330 million light years across. Inside it, there are only about 60 galaxies, in a region of space that, if it were a typical part of the universe, should contain thousands of galaxies. The Boots void is so empty that, when astronomer Gregory Aldering first described it, he said that if the Milky Way were at the center of the Boots void, we would not have known there were other galaxies until the 1960s, because all surrounding galaxies would be too faint to detect with older instruments. When you look at simulations of the cosmic web, you are looking at the largest structures in existence. And what is striking is that this structure, these filaments and voids and clusters, was not random. It emerged from the earliest moments of the universe. In the first few 100,000 years after the Big Bang, the universe was a hot, dense plasma. Tiny quantum fluctuations in the density of that plasma, smaller than you can imagine, were the seeds of everything. Where the plasma was slightly denser, gravity pulled matter together. Over billions of years, those slight density differences amplified. Gas collapsed into stars. Stars clustered into galaxies. Galaxies clustered into groups. Groups into clusters. Clusters into superclusters. Superclusters into the web. The largest structure we can see in the universe is a direct consequence of quantum fluctuations from the first moments of creation. That is not poetry. That is what the physics tells us. Now, all of this, the cosmic web, the superclusters, the filaments and voids, is what we can observe, and the observable universe has a boundary. It is time to talk about that boundary, and why it exists, and why what lies beyond it may be the most unsettling idea in all of science. Part 7. The observable universe and its limits. The observable universe is not the universe. Let me say that again. The observable universe is not the universe. The observable universe is the region of space from which light has had enough time, since the beginning of the universe, to reach us. It is a sphere centered on Earth with a radius of about 46.5 billion light years. The fact that we are at the center of the observable universe does not mean we are at the center of the universe. Every point in space is at the center of its own observable universe. An observer on a planet 10 billion light years away from us would see a different sphere, a different observable region, mostly overlapping with ours but extending further in directions we cannot see. The edge of the observable universe is called the particle horizon. Beyond it, light from those regions has not yet reached us, not because nothing is there, but because the universe has not been around long enough for the light to arrive. As time goes on, in principle, more light arrives from further regions. Our observable universe grows, but here's the twist. The universe is not just old, it is expanding, and that expansion is accelerating. This is where dark energy comes in. Dark energy is one of the greatest mysteries in all of physics. It is a name we have given to the force or property of space itself that is causing the universe's expansion to speed up. We do not know what it is. We do not know why it exists. We know that it exists because we can measure the expansion of the universe, and we can see that it is not slowing down the way you would expect if only gravity were acting, but rather speeding up. About 68% of the total energy content of the universe is thought to be dark energy. Another 27% is dark matter, a separate mysterious substance that we can detect through its gravitational effects but cannot see. Only about 5% of the universe is made of ordinary matter. The stuff stars, planets, people, and everything you can touch and see and name is made of. 5%. Everything you have ever seen, every star in the night sky, every galaxy and every telescope image, every mountain, ocean, book, and heartbeat. 5% of what is out there. And dark energy is pushing everything apart, faster and faster. The consequence of this accelerating expansion is profound. Right now, there are galaxies receding from us faster than the speed of light. Not because they are moving through space faster than light. Einstein's relativity prevents that, but because the space between us and those galaxies is expanding so rapidly that the cumulative effect is a recession speed greater than light. This means that no signal from us will ever reach those galaxies, and no signal from them will ever reach us. Not today, not in a billion years, not ever. These galaxies are not in our causal future. They are, in a very real and permanent sense, gone. And there is a boundary around us called the cosmic event horizon. It is not the same as the particle horizon. The particle horizon marks the edge of what we can currently see. The cosmic event horizon marks the edge of what we will ever be able to influence or receive signals from, even given infinite time. The cosmic event horizon is currently about 16 billion light-years away. Everything beyond that 16 billion light-year bubble is, in a permanent, irreversible sense, beyond our reach. It is outside our universe in every practical sense of the word. And as time goes on, due to the accelerating expansion, more and more of the universe crosses this horizon. The observable and reachable universe is, in a sense, slowly shrinking. Over the next hundreds of billions of years, distant galaxy clusters will fade and vanish from view, their light redshifted beyond detection. Far future civilizations, if any exist, may look out into an almost empty universe, no distant galaxies visible, no cosmic microwave background detectable with conventional instruments, only the stars and remnants of their own local galaxy. We live, right now, in an extraordinarily privileged moment. Part 8. Light is time. Let us slow down for a moment, because there is something I want to make sure is fully landing. When you look at the night sky, you are not seeing the universe as it is. You are seeing it as it was. The moon you see is the moon as it was about 1.3 seconds ago. The light reflecting off the moon and entering your eyes left the lunar surface 1.3 seconds before it touched your retina. The sun you see is the sun as it was 8 minutes and 20 seconds ago. If the sun were to simply wink out of existence right now, in this very second, you would not know for 8 minutes and 20 seconds. You would continue to see the sun shining, continue to feel its warmth for that entire time. And then, without warning, it would simply be gone. The nearest star, Proxima Centauri, appears to us as it was 4.24 years ago. Sirius, the brightest star in our night sky, as it was 8.6 years ago. The Orion Nebula, that stunning stellar nursery visible with the naked eye, as it was about 1,344 years ago. When you look at the Orion Nebula, you are seeing it as it appeared around 680 AD, around the time the Tang Dynasty was rising in China. The Andromeda Galaxy, as I mentioned earlier, as it was 2.5 million years ago. Some of the objects we observe with our most powerful telescopes are so far away that the light reaching us left them when the universe itself was just a few 100 million years old. We are looking at infant galaxies, first-generation stars, the cosmos in its early youth. This is not metaphor. There is a genuine sense in which every telescope is a time machine. And this has a beautiful but melancholy implication. When astronomers study distant galaxies, they study the past. They see stages of galaxy evolution from long ago. And by comparing galaxies at different distances, they are essentially looking at a timeline of the universe. Near galaxies as they are now, more distant ones as they were in the past, and the most distant ones as they were very near the beginning. The deepest images ever taken, the Hubble Ultra Deep Field, and later the James Webb Space Telescope's deep field images, show us thousands of galaxies in a patch of sky smaller than a grain of sand held at arm's length. And many of those galaxies are so far away that their light has been traveling toward us for over 13 billion years. We are seeing galaxies from a time before our sun even existed. The universe is a letter written in light across time, and we are only just learning to read it. But there is a limit to how far back we can read. The cosmic microwave background. At a certain distance, a certain point in time, the universe becomes opaque. For the first 380,000 years after the Big Bang, the universe was so hot and dense that it was a plasma, a sea of charged particles, so energetic that photons of light could not travel freely. They were constantly being absorbed and re-emitted. The universe was opaque. Then, about 380,000 years after the Big Bang, the universe cooled enough for electrons to combine with protons and form neutral hydrogen atoms. This event is called recombination, though slightly misleadingly, since it was the first time, not a reoccurrence. When this happened, the universe became transparent for the first time. Photons were free to travel, and they have been traveling ever since. That ancient light, released 380,000 years after the Big Bang and still filling the universe today, is what we call the cosmic microwave background, or CMB. It was first detected accidentally in 1965 by Arno Penzias and Robert Wilson, two radio astronomers who kept picking up a faint, uniform noise in their antenna that they could not account for. They thought it might be pigeon droppings interfering with the signal. It turned out to be the oldest light in the universe. The CMB fills the entire sky. In every direction you point a sensitive radio telescope, you pick up this ancient radiation. It comes from a surface, the surface of last scattering, that is located about 46 billion light-years away in every direction. It surrounds us completely, and crucially, it is the oldest thing we can ever directly observe. Beyond the surface of last scattering, the universe is opaque. We cannot see further back in time with light. The first 380,000 years of the universe's history is, in a very real sense, invisible to us. We can infer what happened. We have detailed models. We can test them with particle physics experiments, but we cannot see it directly. The CMB is our cosmic horizon in time, and the tiny fluctuations in the CMB, small variations in temperature and density, mapped with exquisite precision by satellites like COBE, WMAP, and Planck, are the imprints of those quantum fluctuations I mentioned earlier. The seeds of every galaxy, every star, every planet, and every living thing in the universe, encoded in the ancient light of the cosmos. We have read those seeds. We have translated them. And they tell us the story of everything. But even this incredible achievement, reading the oldest light we can observe, has its limits. And those limits point to something deeply unsettling about the nature of what we can ever know. Part 9. The privileged moment here is something that very few people have fully thought through. We live in a cosmically extraordinary window of time, not just because life exists, though that is remarkable enough, but because the universe, right now in this epoch, is structured in a way that allows an observer like us to understand its entire history. We can see the CMB. We can detect its fluctuations. We can use it to determine the age of the universe, its composition, its geometry, its history, from 380,000 years after the Big Bang to now. We can observe distant galaxies, thousands of them, at many different distances, and use them to map the expansion of the universe over time. We can detect the large-scale structure, the cosmic web, and use it to probe the distribution of dark matter. We live in an era of astronomical abundance, and we may not always. As the universe ages, several things will happen. First, due to the accelerating expansion, distant galaxy clusters will recede beyond our cosmic event horizon. Their light will become too redshifted to detect. Eventually, the sky will appear to contain only the stars and remnants of our local group of galaxies. There will be no evidence of a larger universe visible. Second, stars will eventually burn out. The long-term future of the universe involves a gradual dimming. After hundreds of billions of years, the rate of new star formation will slow and stop. Existing stars will burn through their fuel and die. The last red dwarf stars, the longest-lived stellar type, will flicker out in trillions of years. Third, the CMB itself will cool. It is already very cold. At just 2.725 Kelvin, barely above absolute zero. As the universe expands further, it will cool further still, eventually becoming undetectable, even to the most sensitive instruments we can imagine. A civilization born in the far future, in 1 trillion years, would look out at an essentially dark sky. The only galaxy visible would be whatever merged remnant of the local group still existed. The CMB would be gone. The evidence of the Big Bang would be beyond any possible detection. They would not know. They could not know. Not without an extraordinary stroke of luck, or some physical record left behind. We know because we are here now. We are living in the one cosmic era when the evidence of the universe's origin and history is still visible, when the large-scale structure is still within reach, when the light from the early universe is still arriving. In this sense, we live in what some cosmologists have called a privileged moment, not in an egocentric sense. Not because humans are special, but because this specific epoch in the universe's evolution allows a sufficiently curious mind to reconstruct the full history and structure of everything. We are standing in the cosmos at a moment when, if we look up and ask questions carefully enough, we can understand it. That is not something that will always be possible. Future civilizations, if they exist, may be permanently in the dark, not because they are less intelligent, but because the universe will have aged beyond the point where its history is still readable in the sky. We are fortunate. And that fortune feels all the more remarkable when you combine it with the scale of everything we have been talking about. Part 10. What we cannot reach and what that means. So where does all of this leave us? We are on a planet orbiting one of 400 billion stars in our galaxy. Our galaxy is one of roughly 2 trillion in the observable universe, and the observable universe may be only a fraction of the total universe, which may itself be infinite. We have sent spacecraft to the outer planets. We have probes crossing the boundary into interstellar space, and it will take them tens of thousands of years to reach the nearest star system, if they were aimed at it, which they are not. With the physics we currently understand, interstellar travel on human timescales is essentially impossible. The distances are simply too vast. The energies required are too enormous. Even if we could somehow build a spacecraft that traveled at 10% the speed of light, 10 times faster than anything we have ever built, it would take 40 years to reach Proxima Centauri. And getting to that speed would require energy on the order of thousands of nuclear warheads for a spacecraft carrying just a few people. Crossing the galaxy, 100,000 light-years, at 10% of light speed would take 1 million years. There are no shortcuts, no confirmed wormholes, no evidence of warp drives. Speculative physics allows for the theoretical possibility of shortcuts through spacetime. The Alcubierre drive, a theoretical construct proposed in 1994, suggests that space itself could be contracted in front of a spacecraft and expanded behind it, achieving effective, faster-than-light travel without violating relativity. But it requires exotic matter with negative energy density, something that may or may not exist. And the engineering challenges are not just significant, they are almost certainly beyond any civilization we can currently imagine. We are, as far as we know, stuck. Not stuck on Earth. We can certainly send spacecraft across the solar system. We can, likely, eventually, send people to Mars. We may one day send robotic probes to neighboring stars. Breakthrough Starshot, a project that has been discussed seriously by scientists and funded in part by tech investors, proposes sending laser-propelled nanocraft to Alpha Centauri at about 20% of the speed of light, arriving in about 20 years. The technology challenges are immense but not obviously impossible. But the galaxy? The local group? Laniakea? The rest of the cosmic web? These are not places we will ever go. Not with any physics we currently know. Not within any timeline that includes us, or our species, or possibly any of our descendants. And beyond the cosmic event horizon, the 16 billion light-year boundary I mentioned earlier, things are even more absolute. No matter what technology we develop, no matter how long we wait, nothing we send out will ever reach what is beyond that boundary, and nothing from beyond it will ever reach us. The universe, vast beyond all our ability to feel, contains regions that are permanently, irrevocably beyond our reach, beyond our knowledge, beyond our light cone. This is not science fiction. This is the straightforward implication of the physics of an accelerating, expanding universe. And yet, here we are. Part 11. The grandeur of knowing. There is a kind of vertigo that sets in when you really sit with all of this. You are a collection of atoms, arranged into cells. Those cells form organs. Those organs form a body. That body has somehow produced a brain. And that brain is capable of understanding, at least partially, the universe it exists inside. You are made of the ashes of ancient stars. The iron in your blood was forged in the heart of a supernova, a star that exploded before our sun was even born. The carbon in your cells was created in the nuclear furnaces of red giant stars billions of years ago. The water you drink contains hydrogen atoms that have existed since the first 3 minutes after the Big Bang. You are the universe looking at itself, and what you are capable of seeing, given what you are made of, is extraordinary. Think about what we have covered. We have figured out that the universe is 13.8 billion years old. We have mapped the large-scale structure of the cosmos. We have detected the oldest light in the universe. We have imaged the shadow of a black hole 55 million light-years away. We have measured the acceleration of the universe's expansion. We have traced the cosmic web from observations of millions of galaxies. We have determined that we live in a barred spiral galaxy with a supermassive black hole at its center, and we have seen that black hole's silhouette. We did all of this from one planet. One small, rocky planet orbiting one unremarkable star, in one of the outer arms of one galaxy, in one corner of the observable universe. The fact that this was possible at all is, I think, as remarkable as any of the distances themselves, because the universe is not required to be comprehensible. Physics did not have to arrange itself into laws that a biological brain could uncover. The universe did not have to be structured in a way that left clues visible to something that evolved for entirely different reasons. And yet it is. And yet it did. The laws of physics, the same laws that govern the expansion of the universe and the rotation of galaxies and the behavior of black holes, are also the laws that govern the chemistry of neurons. The same mathematics that describes the cosmic microwave background also describes the flow of electrons in the circuits of the computers we use to analyze it. We are, in some deep sense, at home here. Not because the universe was made for us, but because we emerged from it. We are not observers standing outside the cosmos, peering in through a window. We are part of it, expressions of it. And when we look out at the distances, when we confront the 93 billion light-year span of what we can observe, when we grasp that there is more beyond even that 96% of the universe is made of things we cannot see or fully understand, when we accept that there are regions we will never reach and epochs we can never observe. It is not diminishing, it is clarifying. Part 12. The Closing Reflection. Let me bring us back to something I said at the very beginning. You are moving right now. Sitting still, you are hurtling through space. Earth orbits the Sun at about 67,000 miles per hour. The Sun orbits the center of the Milky Way at about 514,000 miles per hour. The Milky Way itself is moving through space toward the Andromeda Galaxy and in the direction of the Great Attractor at hundreds of thousands of miles per hour. And beyond that, on the largest scales, the universe is expanding in all directions at once. You are never still. You have never been still. Every second of your life, you have been in motion, riding a planet around a star, riding that star around a galaxy, riding that galaxy through a cosmos that is larger than any human mind was built to fully grasp. And the distances between things in this cosmos are worse than you thought. They are not just large, they are functionally infinite, for anything we might ever want to do. They enforce a kind of cosmic isolation. Our solar system, already vast by any human standard, is a tiny island in a sea of interstellar emptiness. Our galaxy is one of 2 trillion, and the universe beyond the observable boundary is simply gone, unreachable, unknowable, beyond any future technology. The distances also enforce something else, a kind of humility. Not the despair kind of humility, not the meaninglessness kind, the awe kind, the kind that makes you go outside on a clear night, lie down in the grass and look up, and understand, really understand, that those points of light are not decorations. They are suns, and many of them have worlds, and some of those worlds may have oceans, and some of those oceans may have life, and some of that life may be looking up at its own night sky right now, wondering the same things you are. We do not know if that is true. We have not found it yet. The distances between stars make communication between civilizations extraordinarily difficult, and contact nearly impossible, even if intelligent life is common. The universe may be full of civilizations that will never hear from each other, separated by gulfs too vast to bridge. But we are still asking, still looking, still pointing our telescopes at the darkness and asking what is out there. And that asking, that curiosity in the face of an inconceivably vast and indifferent cosmos, is one of the most extraordinary things in the known universe. Part 13. The final stretch we began with the solar system. A basketball sun with a grain of sand Earth 86 feet away, and a tiny marble Neptune a mile and a half out. And the edge of the Oort Cloud, the real edge, somewhere between 700 and 800 miles from our basketball. A solar system so vast that our fastest spacecraft will spend thousands of years just crossing it. Then we crossed into interstellar space, the 25 trillion mile gap to Proxima Centauri, a crossing that would take our fastest spacecraft over 6,000 years. Then we pulled back to the Milky Way, 100,000 light years across, 400 billion stars, a supermassive black hole at the center, our solar system quietly orbiting in a suburban spiral arm, completing one lap every 225 million years. Then the local group, the Virgo supercluster, Laniakea, stretching 520 million light-years, containing 100,000 galaxies, all gently flowing toward the Great Attractor. Then the cosmic web, filaments and voids on the scale of hundreds of millions of light-years, stretching all the way to the edge of the observable universe, 46.5 billion light-years away in every direction. Then the edge itself, the particle horizon, the cosmic event horizon, the boundary beyond which nothing can reach us, and beyond which we can never reach. And beyond that, the universe, extending for perhaps infinite distance, containing perhaps infinite versions of everything, or perhaps not. We cannot know. We will never know. The distances in space are worse than you think. But here's what I want to leave you with. The universe is not hostile to you. It is not trying to make you feel small. It is just what it is. Unimaginably vast, ancient, structured, beautiful, strange. And you are part of it. Not a visitor. Not an accident. An expression. A temporary, conscious expression of a cosmos that has been building toward the complexity needed to ask questions about itself for 13.8 billion years. The atoms in your body were in stars before they were in you. The carbon in your cells has been through multiple stellar cycles. The calcium in your bones was forged in the nuclear heart of a massive star that exploded before our solar system formed. You are 13.8 billion years old in your atoms. You are the latest chapter in the longest story. And from where you stand, on this small, warm, improbable world, you can see 46.5 billion light years in any direction you choose to look. That is not nothing. That is extraordinary. Part 14. Before you go, I want to plant something in your mind. We talked today about the distances, the cosmic scales, the fact that most of the universe is beyond our reach. But there is a question we have been circling without fully landing on. If the universe is this vast, and planets are this common, and the chemistry of life is built into the fabric of the cosmos, then where is everyone? The Fermi paradox, the great silence. Why, in a universe with 2 trillion galaxies, billions of years of history, and trillions of potentially habitable planets, have we heard nothing? That question has answers, several of them, and some of those answers are deeply unsettling in ways that make the scale of the universe look comfortable by comparison. We are going to go there next. If that sounds like something you need in your life, hit subscribe, turn on notifications, and I will see you in the next deep dive. Until then, keep looking up. If this video hit you in the chest the way I intended it to, share it with one person. Not just anyone, the one person you know who stares up at the sky and asks questions. The comment I want to read from you is this. After everything we talked about tonight, what is the scale fact that you genuinely cannot stop thinking about? The one that keeps returning? Leave it below. I've read every one of them. Links to further reading, recommended books, and the sources for this video are in the description. Everything there is worth your time. Stay curious, stay humble, and remember that the universe is under absolutely no obligation to make sense to us. It just does. If you enjoyed this exploration of our ever-moving universe, please like the video and subscribe for more relaxing science documentaries. I'd also love to hear your thoughts in the comments. What fact about motion in the universe surprised you the most? Thank you for spending this time exploring the cosmos with me. Sleep well, and I'll see you in the next journey through science and space.